Hi there. Today we are diving into the Monotone Convergence Theorem, or MCT. It is a powerful tool in analysis that helps us prove a sequence converges without needing an explicit formula for the nth term. Let's get started. The Monotone Convergence Theorem is elegant. It says that if a sequence is monotonic, always moving in one direction, and remains within a bounded range, it is forced to settle at a single value. Imagine the sequence as a hiker climbing a hill. If they can only go up, but there's a solid ceiling above them, they must eventually find a plateau. That plateau is the limit. This theorem is the bridge between qualitative behavior, the direction of the sequence, and the quantitative value, the limit itself. Always remember, monotonicity plus boundedness equals guaranteed convergence. To use the monotone convergence theorem, we follow a simple three-step checklist. This workflow turns a complex problem into an organized strategy. First, prove the sequence is monotonic. This means showing that every term is either greater than or equal to, or less than or equal to the previous one. Second, prove the sequence is bounded. We need to confirm it stays within a specific interval, so it cannot grow infinitely. Finally, once convergence is guaranteed, we can find the limit by setting the sequence to a fixed point, where f of L equals L, and solving for L. Let's look at a square root recursion. We define the sequence with a first term, a 1 equals the square root of 2, and the next term is defined as the square root of 2 plus the previous term. We want to prove that this sequence converges to a limit using the monotone convergence theorem. To prove our sequence is increasing, we start with the base case. We check the first two terms of our recursive sequence. A1 is the square root of 2, roughly 1.414. A2 is the square root of 2 plus the square root of 2, which is approximately 1.848. Since 1.848 is clearly greater than 1.414, the base case is satisfied. To complete our proof by induction, we assume the relationship holds for some index k. That is, we assume ak is greater than ak minus 1. Since the square root function is strictly increasing, adding 2 to both sides and taking the square root preserves the inequality. This directly implies that ak plus 1 is greater than ak, confirming the sequence remains increasing for the next step. Now we check the boundedness condition. We want to see if our sequence stays below the value 2. This is the first step of our proof. Our sequence starts with a1 equals the square root of 2, which is approximately 1.414. Comparing this to our boundary of 2, it is clear that 1.414 is less than 2. Visually, we can think of 2 as a ceiling. Since our starting point a1 is below this ceiling, the base case is satisfied. Now we move to the inductive step. We assume that our term ak is less than 2, and we want to show that the next term ak plus 1 is also less than 2. Given our recursive definition, ak plus 1 equals the square root of 2 plus ak. Because we assume ak is less than 2, replacing it with 2 makes the expression larger. This simplifies the root to the square root of 4, which is exactly 2. Therefore, ak plus 1 must be less than 2. This confirms that our sequence is bounded above by 2 for every single term. Now that we have verified our sequence is both increasing and bounded above, we move to the final step of our process. The monotone convergence theorem acts as our bridge. Because these two conditions are met, the theorem guarantees that the sequence must converge to a specific real number limit, which we call L. With this existence confirmed, we are now ready to perform the algebra to actually calculate the value of L. Now we solve the quadratic equation. Factoring L squared minus L minus 2 gives us the product of L minus 2 and L plus 1 equal to 0. This gives us two potential roots, 2 and negative 1. However, our sequence consists of positive terms only. Therefore, the limit cannot be negative, and we must discard negative 1. This leaves us with our final result. The limit of the sequence is exactly 2. Now for something different. Let's examine a fractional recursion. x1 equals 2 and xn plus 1 equals 1/2 times the sum of xn and 3 divided by xn. This is a classic method, often called the Babylonian method, used for estimating square roots. Specifically, this sequence converges to the square root of 3. To prove the sequence is bounded below, we use the arithmetic mean geometric mean inequality. For any positive xn, the average of xn and 3 over xn is at least the square root of their product, which simplifies to 2 root 3. Therefore, xn plus 1 is always greater than or equal to the square root of 3. This proves our sequence is bounded below by root 3. To prove our sequence is decreasing, we look at the difference between consecutive terms. Substituting our recursive formula, we simplify the expression to 3 minus x sub n squared, all divided by 2 times x sub n. Because our sequence is bounded below by the square root of 3, x sub n squared is always at least 3. This makes our numerator non-positive, confirming that each term is smaller than the previous one. Because our sequence is both decreasing and bounded below by the square root of 3, the monotone convergence theorem confirms that a limit L must exist. We have now proven the existence of the limit. Next, we will calculate the final value of this limit. Once we establish that the sequence converges to a limit L, we can substitute L for both xn plus 1 and xn in our recursive formula. Next, multiply both sides by 2 to clear the fraction. Subtract L from both sides and we reach a simpler form, L equals 3 divided by L. Multiply by L and we get L squared equals 3. Since all terms in our sequence are positive, the limit must be the positive square root of 3. When working with the monotone convergence theorem, there are a few common traps that students often fall into. First, never assume a sequence is monotonic or bounded just by looking at the first few terms. You must prove these properties formally. Secondly, remember that rigorous proofs often require mathematical induction. Skipping these steps can lead to flawed conclusions. Always remember the teacher's tip. Proof is the foundation of the theorem. Don't apply the theorem until you have verified both conditions. Why is the monotone convergence theorem, or MCT, so important in mathematics? Think of it as a vital bridge. It connects the qualitative behavior of a sequence, how it moves over time, to the quantitative specific limit value. In numerical analysis, this theorem is essential. It guarantees that a process will settle into a stable value, allowing us to trust our computational algorithms. By mastering MCT, you turn vague patterns into precise results. It is the ultimate tool for proving convergence. The monotone convergence theorem isn't just for textbooks. By 2026, it is vital for modern computational tools. First, in formal proof assistants like Lean, we use MCT principles to let computers automatically verify the validity of complex mathematical proofs. Second, it ensures numerical stability in algorithms. It guarantees that our calculations don't drift away into error, maintaining precision in every iteration. These modern applications turn MCT into a bridge between pure analysis and the reliable code running our digital world. To wrap up, let's look at the golden rules for the monotone convergence theorem. If a sequence is increasing and bounded above, it converges. If it's decreasing and bounded below, it also converges. When you apply this to a problem, always follow this workflow. First, prove the sequence is monotonic using induction. Second, prove it remains within bounds. Finally, set your recursive function equal to L to solve for the exact limit. To master the monotone convergence theorem, remember this crucial shortcut. When you're ready to find the limit, treat it as a fixed point. Since the sequence converges to a limit L, both the input and the output of your recursive function approach that same value. By setting L equal to f of L, the recursive relation collapses into a simple algebraic equation. This works because convergence implies the difference between terms vanishes. It transforms a dynamic sequence into a static algebraic loop, saving you from complex calculus. Keep this fixed point trick in your toolkit, and you will navigate recursive limits with ease. Happy calculating! You have officially mastered the monotone convergence theorem. Remember, it is more than just a calculation tool. It is the vital bridge connecting a sequence's behavior to its limit value. Keep these 3 pillars in mind whenever you face a recursive sequence. Always define your domain, Never skip your induction proof for boundedness and algebra to find the final result. You have done great work today. Calculus is a journey, and you are well on your way. See you in the next lesson.